Our first talk today is by Jacques Vanneste, one of our Mercator fellows, and we're happy to have him presenting the imprint of ocean currents on surface gravity waves. One comment concerning the questions: we will have a short question session after each talk, but there will also be a general Q&A session at the end of the session. So some of the questions might be deferred to a later time at the end of the session. All right. So that's it so far. And Jack, floor is all yours.
Thank you. Thank you for the organizers for the invitation. Okay, so I'm going to talk about surface gravity waves. I think I'm the only speaker talking about this. I'm by no means an expert, but I'm working with experts. So this is work John Lewis, Bia Villas-Boas, School of Mines in Colorado, Bill Young at UCSD, and Han Wang, who's working with me at Edinburgh. So the question is, I have not magic fingers. Okay, so first, yeah, just to set the scene, just let me remind you about surface gravity waves. So they look like this. This is my only opportunity to cite a paper from the Surfer Today journal. It doesn't happen often. And the dispersion relation, thanks, is given by this, right? So the frequency sigma, that's the classical notation, goes like the square root of the magnitude of the wave number. So brief motivation, why do people care about surface gravity waves? Well, clearly they're important for air-sea interactions, the exchanges at the surface of the ocean between the ocean and the atmosphere. Something I'm interested in is surface transport. So waves induce Stokes drift, which contributes to transport of material. There's also some mixing aspect. And then finally, what drives all of the research actually is important for shipping and for surfing, okay, and other leisure activities. All right, so what my interest is here is in what is the effect of current at the surface of the ocean on those waves. And so you can imagine that there are some effects of currents. The first effect will be transport. Waves will be moved about by the currents. Another effect will be refraction by current gradients. So the medium on which the waves propagate is inhomogeneous, so you expect refraction. And then there's also an effect of Doppler shift. Okay, and so one way of thinking about that is what really controls the wave amplitude is a conservation for the wave action, which is this A here. So this is wave action, like we saw yesterday in Georg's talk, on in a full phase space. So it depends on position and wave number. And there's a relationship between wave action and the energy density, which is you have to divide by the intrinsic frequency, right? So Doppler shift means that sometimes things are simple for wave action, but they're more complicated for the energy because the Doppler shift introduces a change between the two quantities. Okay, so here is the wave action conservation equation. So I have no sources, everything is assumed to be linear as well. So where does the current sit? Well, it's in this absolute frequency omega, right? So omega is the intrinsic frequency plus the Doppler shift term. So every time there is a U, there will be the potential for the influence of the currents on the surface waves. Otherwise, I mean, those terms should be familiar. So this first term here is just transport by the group velocity, which now has the flow velocity as part of it, and then there's this refraction term. All right, so I'm going to talk mostly about the effect that the currents have on significant wave height. Significant wave height is what people in the field use to measure wave amplitudes, and it's simply 4 times the surface elevation root mean square. Okay, the 4 is there for historical reason. I'm told this because when you're on a ship and you try to estimate the wave height, you mostly see the tallest waves, and so there's a kind of bias. And so that's essentially just the energy at a given location. So you take the energy density, you integrate over wave number, and you squeeze in a little g there. Okay, so the question is, what is the effect of currents on significant wave height? And this paper sort of gives an answer. It says that ocean currents have a large effect on the wave heights. Okay, so I like the paper because it's with motivation. So what they did is that they carried out some simulations of both the the flow. So this is the east coast of the United States. There's the Gulf Stream. I'm just showing here. They're just showing the magnitude of the velocity. So you see the Gulf Stream. You see some vortices, and then they carried a wave simulation by solving this wave action equation. So using a classical wave model, and they compare the situation with and without the current. Okay, so let's look at without the current. The bottom left here, you have waves coming from the open ocean and a fairly homogeneous, significant wave height field. Okay, not much happens. Then when you switch on the currents, you see all those interesting features, right? So there are large variations, so you don't see the scale, which somehow doesn't show. The mid-range here is 1.5 meters of significant wave height, and there are fluctuations of the order of 60% or something like that. Okay, so they're fairly large fluctuations, and you can start looking at where they are. So like this feature here is correlated with this vortex. You can see that behind this vortex, there's kind of a wake. There's not too much just above the Gulf Stream itself. Okay, so the aim is to try to explain this in as simple a way as possible. So another paper which looked at this in detail is this paper by Villas-Boas et al. And so they did more idealized simulation. So let's just look at the left panel here. So this is a velocity field. You probably can't make out the arrows, but you can see the color, which is just the magnitude of the velocity field for a kind of random turbulent-like current. And then they had a wave maker creating waves on the left, propagating towards the right inside this domain. And what you see here is a significant wave height as a result. Okay, so here the mean is 1 meter, and you have again fluctuations, in this case of the order of 20–30%. And you see those long streaks essentially behind the vortices, okay, in the kind of wake of the vortices. And the reason there are several panels here is because they looked at the relative importance of vorticity and and divergence on the wave field. So they created a synthetic velocity field with the same statistics for the magnitude of velocity, but a mixture of a potential flow and a vertical flow. So doing Helmholtz decomposition. So here you have purely vertical flow. Here you have a purely potential irrotational flow. And you see that that has a very strong impact on the wave field. A flow without vorticity doesn't do very much at all. Okay, so the wave field remains homogeneous. So that's something you want to also explain. So our aim here is to make predictions for this change of wave height. And at the moment, what I'm going to talk about is the effect of just a single flow feature, so something which is localized in space. So really it becomes a problem of scattering, right? So you have waves incident to a flow feature, say a vortex, and you want to know what is the response. It's really a scattering problem. Okay, so what is my scattering problem? So we will start, just like in those simulations, with an incident wave field, which is pure, well, not pure plane wave, but homogeneous in space. I'm going to focus on swell. So swell are those waves which are very long, it's kind of almost plane wave-like, a bit like here. But I'm not going to assume a plane wave. I'm still going to assume some kind of spectrum with a non-trivial directionality. So waves are excited which propagate in different directions. But swell means a very narrow spectrum. So both narrow in the magnitude of the wave number, so that's narrow in frequency, and narrow in this angular direction. Okay, so this picture is an example of that. So this is a spectrum presented in the wave number plane. You see this power here is spread, well, there's some spread both in the angular direction and in the frequency or wave number direction. So that's my interest. And so, as I said, this is the kind of typical look that you get. So the waves vary parallel to the crest, but not enormously. Okay, so there is a clear kind of anisotropy. So swell is what you get when you are a long distance away from the source of generation, because the kind of dispersion effect means that you tend to get fairly narrow spectra. And then, of course, in this problem, there is a kind of obvious small parameter, which is a Mach-like number. If you look at the ratio between the velocity of the flow of the current and the velocity, the groove speed, well, it's typically very small, right, of the order of 10 to the minus 1 or less, because when those waves travel rather fast, things like 10 meters per second, the currents are much slower. Okay, so I mean, this is a kind of very strong. There's not much to assume. I mean, this holds pretty much in all cases. Okay, so our assumptions are we have this spectrum of incident waves, which I denote by A star, and the statement that it's fairly narrow. I just encode this by saying that it depends on k minus k star. So k star is a peak wave number divided by a small parameter delta, and similarly in the angular direction, there's a small parameter delta. Okay, so I mean, just the schematic here, we are shooting waves hitting a flow feature, a vortex, and we ask what is happening behind. And this is sort of ray tracing version of this. We don't think too hard about ray tracing because we don't have plane waves here. So at each point, we have in fact a spectrum of waves going in all directions. So we have two small parameters. One is the narrowness of the spectrum. The other one is this Mach-like number. So you have to ask, what's the relationship between the two? It turns out that the most natural thing to do is to assume that they have the same order. Jonas, yeah?
Is that same
yeah, well, they're pretty much linear waves propagating onto medium at rest, and then the flow is a small perturbation to that. So this is not the velocity. This is the velocity of the current, right? But I mean, you're right. We also assume linearity, right? So we don't worry about non-linear effects. Okay, so you can just take this wave action equation, look at the small parameter, and realize that well, there's a lot of simplifications, even though it's an equation in four spatial, well, space-like dimensions, right? So there's two spatial dimensions plus two wave number dimensions. You can actually simplify it to not very much, and you realize that's what you have to. What's left is some simple exercise in matched asymptotics, where there are really two regions. One is the region above the flow feature, and then the other one is the region far downstream. And above the flow feature, there's some kind of changes, but really what matters is that far downstream, the change in spectrum that has been induced above the flow feature are going to have an effect because of focusing and defocusing of waves. Okay, so we have two regions. One is this inner region. This L here is just the scale of the flow feature, say the radius of a vortex, something like that. And we can just write down exactly what the action is like. So it's the incident action, and there's a shift in the wave number, which depends on the velocity. And there's a shift in the frequency, which depends on the integral of the derivative of the velocity along the direction of propagation of the waves. Okay, so this is all very explicit. This shift here is really important in the sense that you can tell it's sort of reversible. When the velocity goes back to zero, this shift reverts to zero, right? So there's no cumulative effect. Whereas this one here, that's not the same, right? When you go at a large distance x away from the downstream of the flow feature, this has a non-trivial influence. So there's a net change in the spectrum downstream of the vortex, which has an impact a long distance downstream. And if you look now at the significant wave height, you have to integrate this as in wave number and angular with respect to the wave number and the angle. And because these are just shifts, you get the same answer. Okay, so the prediction here is that just above the vortex, there is no effect. If you look only at significant wave height, it just stays what it was. So the interest is what's happening in this wake region, so a long distance away from the vortex, where now you have a cumulative effect coming from the so there's a small deflection essentially of the waves, and then the small deflection has a large impact if you go further, well, far enough downstream. Okay, so here's what the action looks like. So as far as the wave number is concerned, there is no effect, but then the angular distribution has been changed by this quantity here, delta, which is the angular deflection immediately after the vortex. So this is by how much the angles of all those waves has changed. And we have to evaluate this as a function of x. Okay, so this angular deflection is something very simple. It's simply the integral of the vorticity along the coordinate parallel to the wave propagation. Okay, so you just have the waves are going to travel through this vortex. They integrate the vorticity on their way, and at the end, the deflection that they experience is just this total vorticity that they've experienced. All right, so once you have this, then you can get the significant wave height by integration, and now you have some non-trivial effect. Okay, so now you're going to have some significant wave height change. Right, so this is very simple theory. So linear, and everything is very explicit. We want to test this with our version of reality, which is numerical simulations using WAVEWATCH 3, which is one of those models solving the wave action equation. So this is non-trivial numerics, right? So we're solving a PD in a four space-like dimension, space-time. We're going to do this in a very simple setup where we have a Gaussian vortex to start with, and our spectrum is also taken to be Gaussian. Okay, so as promised, it's peaked around a certain peak wave number, and also peaked in frequency. So it's almost in the x direction. So typical parameters here, our group speed for the waves is 8 meters per second. We're going to look at two different velocities, 40 centimeters and 80 centimeters per second. So these are kind of strongish, but not ridiculously small flows. And nonetheless, I mean, you can see immediately that this Mach-like number is going to be small. And then we're going to look at this parameter S. S here controls the width of the spectrum in the angular direction. It's a key parameter. So S large means that you have a very narrow spectrum, so almost a plane wave. All the waves are in the same direction. S not so large means a broader spectrum. And it turns out that S is never ridiculously large in reality. So typical values would be 10. We push this to 40. We're going to push this even further just for demonstration. So the parameter delta, which is the angular spread, is given by this. So it takes smallish, but not really very small value. So we're doing asymptotics while having small parameters which are not terribly small. Right, and so what I'm going to show is not the significant wave height, but the anomaly. So I'm just removing the incident value, which in our case is 1 meter. Everything is linear, right? So you can just scale that. Okay, so here's the kind of picture that we get. So these are 4 rows. Each row is for a different set of the 2 parameters. So the width of the spectrum and the maximum velocity. The vortex is this little dashed circle. And you see this large-scale pattern emerging. In this case, the spectrum is fairly broad, and so you get a kind of fairly broad wedge. You get high values for the significant wave height on one side. This is kind of convergence of the rays, if you think of rays. And on the other side, you get divergence. Okay, and so really the summary is that our asymptotics is doing pretty well. Our amplitudes are a bit larger than what the model is. It's hard to know who's right. I mean, the model can probably be a bit dissipative. Our wake is sort of more marked, right? This one is a bit more diffuse, which is probably a problem of having a finite box in which you do the simulation. Okay, so everything works pretty well. So the simple formula reproduces the as close as we can to reality. You can look also at not only at the significant wave height, but you can look at the spectrum itself. right? We both predict the full spectrum, the action spectrum. And so what I'm plotting here is the action spectrum integrated in the wave number direction. Okay, so this is the result is how much action there is at a given location for a given angle of propagation. And so what I'm showing here is, again, this is the numerical simulations with WAVEWATCH. This is the asymptotic prediction as a function of, so I fix x, that corresponds to each row. So x is the distance along the direction of propagation as a function of y and theta. So this is kind of a cross section. You're seeing this wave spectrum, which initially is just a Gaussian in theta, is being deformed by the action of the vortex. And then there's this kind of important sort of overturning happening, which means if you think about the significant wave height, you obtain it by integrating this along theta. Okay, so you're going to get larger values here than you are here, right? Because the overturning means that you kind of get twice as much wave action. So that's the reason. I mean, you can interpret what the results in this way. Okay, now if you know a bit the literature on this, there's a lot about caustics. So caustics strictly they arise when you have a purely monochromatic wave. Okay, so that's the limit where so S, this parameter controlling the width of the spectrum, goes to infinity, or the delta, which is essentially 1 over S, goes to 0. So you then have a spectrum which looks like a Dirac. Okay, this delta is not the same delta as this one, but in proper Dirac. It's a Dirac in wave number and in the angular coordinate. Then the response is also Dirac. Okay, everything is just localized. And according to my formula, which works in this case, here is what you get. Okay? And now you can ask yourself, if I integrate this with respect to theta, what do I get to obtain the significant wave height? And you realize that there's going to be a problem, very large amplitude, in fact, infinite amplitudes, at the location where, well, essentially, so if you think of this, which is where this Dirac vanishes, okay, that's a map for each x and y, you can find theta. Essentially, it says for each x and y, there is one ray going through. This map is singular at some points. And these are the location of the caustic. So maybe it's best explained on those pictures. The caustic situation is the one where you have very narrow spectrum, like here, right? Very narrow band, almost localized on a curve. This curve is overturning. And then the points, those 2 points here and here, where the tangent is vertical, is where infinite number of rays, if you like, are meeting. That's where, according to kind of most basic theory, the amplitude is infinite. In fact, the amplitude goes like my parameter s to the 1/4. Now, on the previous pictures, okay, I had plotted the location of the caustics. I can tell you this. This is what those curves are. And you saw that the caustics have nothing to do with the wave response. Okay, so that said that caustics are irrelevant here. The reason is that the spectrum that we have, although narrow, is still too broad for the caustics to show up. So if we push things very hard, so we take a really narrow spectrum, so this is completely unrealistic, and this is even more unrealistic, then the response that we get starts to indicate the relevance of caustics. Okay, so for this super large value, indeed, the largest response is localized on those caustic curves. So the message here is that caustics are all kind of interesting and nice, but for a reasonable wave spectrum like the one you see in the ocean, they're just not going to be significant. Okay, just a final little game. As we've seen, I mean, the response is controlled by the vorticity integrated along the path of the waves. And so you can ask yourself, are there interesting situations where this vorticity is going to integrate to 0, for instance? And an obvious example is just look at a dipole. So if you have a dipole, you can have 2 dipoles, one which is aligned like this one with the direction of the wave propagation, and one which is perpendicular, like the one at the bottom here. And the response you expect to be completely different because, well, simply if you follow the waves, in the first case here at the top, you're going to get some non-zero value, right? So the integral of the vorticity, which is here shown in green and purple, is going to be non-zero. So you're going to have some interesting deflection and interesting response in a single wave height. Whereas if you have this dipole, the integral encounters first positive vorticity, then negative vorticity. It's going to be a cancellation. The integrated vorticity, my delta here is going to be 0. Okay, so it's a very simple prediction. And then you can see that it's kind of verified. So we've just done the same exercise, so shot some waves from the left here, let the waves encounter this dipole. I'm showing here the WAVEWATCH simulation result in our asymptotic prediction, and they match very well. You get this interesting pattern. In the case of the dipole aligned in the y direction, there's a very weak response for WAVEWATCH, and according to a theory, there's just no response at all. Okay, so this is a form of cloaking, right? So people like this in wave propagation, where you have some object, you shoot waves through this object, and yet this object is completely transparent. Okay, so here it's just objects such that vorticity integrates to 0 when you integrate along the wave. Okay, so some conclusions. So what I've shown here is a very simple asymptotic theory for the response of the wave action spectrum or the wave energy spectrum to a localized flow feature. And so I've been assuming that this Mach number is very small. As I said, I mean, this is really completely obviously true in realistic situations. And then I've taken the situation of a swell, so a wave spectrum which is localized in both the angular direction and in frequency or wave number. That parameter is never super small for realistic swells. Okay, so we found this good match between the full-blown simulation of the wave action equation in our very simple formula. So we've done this vortex, we've done dipole. With the formula, of course, you can experiment with any current you like, right? It's very easy. The key message is that in this approximation, the only thing that matters is the vorticity integrated along the flow. I mentioned at the beginning this big difference seen in simulation between having a flow which is vertical and one which is purely potential, purely divergent. Well, it's kind of obvious. If you have a flow, even very strong, which is completely with 0 vorticity and purely divergent, there's going to be no response as far as the wave field is concerned. So I mean, one motivation for studying this is that people are hoping to retrieve currents from observation of significant wave heights or wave fields. So some instruments can estimate the roughness of the sea, which is some kind of measure of the energy of the waves. And so there's a hope that you can just look at this roughness of the sea and find out what the currents are. Well, obviously, this is not terribly good news, because what you perceive from the currents is some very limited information. You just perceive some kind of integrated vorticity. There's a lot of information which is being lost. You would have to kind of experiment with waves going in all directions, for instance. So it's a bit like tomography, where you have to scan someone's body from different angles to get information. So there are two limits, right, to what I've shown. I mean, one is the caustic limit, not quite realistic. The other one is kind of linear regime, where epsilon is much smaller than delta. I haven't talked about this, but then it becomes super simple. I mean, it's just incredibly cheap. You can, the anomaly in things like wave height is just some linear map of the velocity. And in fact, for that regime, you don't even have to assume that you have swell-like behavior. Okay. That's my talk.